Hey everyone, I thought I'd make a video solution of number 63. We did it today in the Zoom, so maybe that's enough, but it may be worth talking about it again. It is a hard one to do, but more than that, in the Zoom, I told people to look up the formula here, and I couldn't find it online. Usually I tell people to look in the back of the book, so I looked this up and then printed it out, and here it is. This is the integral, and I was doodling with it. It looks like you could do an integration by parts, but even then, once you do that, you get this little piece, and then that would be a trig integration. So this is a pretty hard integration as far as I can tell. So I was debating about doing it with you, but I go, you know what? No, I'm just going to say look it up. And that's why the Appendix B is there. And that's what I was saying, and will always say for homework or for the test. Just kind of look it up. And the book does a good job in Appendix B, but this one was not there. And it kind of threw me off, and I needed some better books, and I'm not in the office, and so I couldn't get my normal book, so I kind of had to use Google, and anyways, and we came across a different solution that has the sinh, and the inverse sinh is a natural log, so you'll see it if you look at the video ones. But hold off on this. I'm going to put this off to the side, and let's just run to the physics first before we hit the math here. The problem says a disk of radius capital R, so I'm going to try to make a disk here by giving kind of a side view down the axis of symmetry. I'll call this the x-axis, and maybe to match their picture, I'll try to give it a little bit of thickness, but not enough that it becomes an issue. I think they want us to just deal with the it being a disk. They don't say a cylinder. But here's the big part, is it has a non-uniform charge density sigma, which equals to some constant times r, where r is measured from the center of the disk, so moving outward. Then it says here, by direct integration, find the potential at this point P, which they say is a distance x out on the axis of symmetry here. And so I like to describe it this way, that what I'm going to do is say that the potential of a disk comes from the summation of the potential of a bunch of rings. So I'm going to add up a bunch of rings. And so maybe drawing this in green, I'll say here's a ring, here's another ring, here's another ring, and I'll start with the inner small ring and just get bigger and bigger and bigger until we get to the radius of the disk, which maybe I should put that in the drawing. They said the radius of the disk is capital R. So clearly don't confuse little r with big R. Little r is the measured from that center up. Now, let's talk about the potential from a ring. Now, in the Zoom, I went ahead and re-derived it kind of as a review. But for this video solution, I won't. You can look at the Zoom if you want, but it's also done for you in the textbook. It's example number 5. It's probably best if I don't, because I think that's what the author wants. And it comes out to be the Coulomb's constant times the charge on the ring. Maybe actually just look up the example 5. I don't want to take too much time out of the video here. I think I can find it real quick. Yeah, so here's 3, example 4, example 5. And your author comes up with, and he calls this capital Q, but it's really the charge on the ring. And I want to be careful with that, because I don't want you to confuse this capital Q with maybe the charge on the disk. And then it's divided by, And your author writes it as a squared plus x squared, where the x is the same as in this picture, how far along the axis of symmetry, but the a is the radius of the ring. See, here's why I say that, because for this problem, to get the potential of the disk, we first have to say that we're adding up an infinite number. It's not just like 1 to the n, and maybe n is 3 or 4 disks, but we're going to have a bunch of green disks that are going to be infinitely thin and an infinite number of them. So maybe I should say infinitesimally thin and an infinite number of them. So that's going to change a summation into an integration. And so then we will have the potential from a ring. But maybe I'll first write it as a small potential, because this potential of our ring is made from a really, really infinitesimally thin ring, and so an infinitesimally amount of charge is on it. So that's why what I need to do is to say, okay, when I make this ring thinner and thinner and thinner and thinner, what gets smaller? And what gets small in this equation is not the x, it's not the a, it's the charge on the ring. And it's kind of convention to use a lowercase, so even though it was derived in an uppercase q for the charge on the ring, usually when we do an integral, we are talking about a small amount, so I'm going to put a dq. But I want you to notice then that this might be a trickier part of the problem, recognizing what is getting small as this ring gets thinner and thinner and thinner. And so if you imagine a thin ring here, maybe I'll just darken this one in. So there's a dark green ring. A is the radius of the ring. As it gets thinner and thinner, A doesn't go to 0. And certainly it's not X that go to 0. X is the same distance away no matter which ring I'm working with and no matter how thin it is. And I think you're just so used to your calculus to having like a dx here. You're tempted just to put a dx here, but don't. That's not what goes to 0. This is the same skill set that we were talking about starting in physics in chapter 23, and we saw it, well, a lot in 23 and a little bit in 24, but now we're seeing it again. We just got to add up a bunch of rings, okay? So be careful with this step. And so this is what I'm working on, and this is a little different approach than I did in the Zoom. And so I thought this would be good and better. And of course, most importantly, I thought it'd be a good chance to actually show you what I didn't quite finish in the Zoom, which is this integral. Okay, so anyways, this is where reading the math comes into play. What's really going on with this math? Okay. In fact, I should probably also continue to read the math, because I got this K and I got this dq, and I'll even put charge of ring here so I don't forget. But down here in the denominator, this A came from the textbook solution, where they used the radius of the ring as an A. But if you come back to this problem where they're measuring little r from the center of the disk outward, we should probably then say, well, each ring has a bigger radius and call it little r. And of course, big R is the radius of the whole disk, but the little r is a variable of adding up a bunch of rings. So it would seem most appropriate to change the A, which again was derived in example 5, to an R, and I do that just because I'm reading what the math means. I see this and they've worked it out. But what it means is not so much what the variable is. It's not just an A and always an A. A is the radius of the ring. And in this problem, radius of the ring is best represented by R. So I'm just going to change the A to an R. That's my justification of it. But again, it's not that I'm doing any math. I mean, I guess you could say A equals to R and say, okay, I am doing some math. But I've got to really understand what A is and what I mean by this R in order to make that step. And so that's why I keep saying, make sure you're reading that math, not just doing the math. And, you know, really that Q was that same thing. This was really the Q of the ring. And now we're talking about our calculus, and we're taking an infinitesimally small amount of charge because the ring gets thinner and thinner. And so that's why the dq goes here. All right, so this is actually the integral we want to do. Now, it's still hard from here forward because now I'm going to come back here to this charge density. The charge density is charge per area. And in this case, since I want the charge of a ring, let me put, again, a Q of a ring, and that means it must correspond to an area of a ring. Now, maybe I'll look on face down on this disk. If I had this disk like here, and here's the center, and I'm looking at one of these green disks, green rings here, maybe like this, and I'll give it a little bit of thickness. Again, here reading the math, what I mean in this integral is this is the charge on the ring. So this is the charge, the total charge on this whole ring, which has got an infinitesimal thickness. And I then am going to use this to say I can replace the dq with a sigma dA. Where, again, of course, sigma the charge density, but dA is the area of that ring. And so that's an important step, changing this integral from a dq into a dA. And even then, I still have another important step to make, which is to change the dA into a dr. And I'm going to do that with a little bit of geometry. Maybe back here in this picture, imagine cutting this green ring and laying it straight. Its area would be its length times its width. And now that would really be dA, the area of the ring, now that I laid it out. And its length would be its circumference, 2 pi r. And then again, lowercase r, because, you know, this ring here would have a radius out to there, but other rings would be a bigger circumference. They would be a bigger r going out. And eventually, of course, the last ring I would add up would have a circumference of 2 pi and be capital R. So the first ring would have a radius of 0, and the last ring would have a capital R. So that's the length of it. And then the width of it would be how thick this is, and that would be the dr, right? That would be an infinitesimal thickness in this direction, which is the r. So there's the length times the width. So then I can take this equation here and say, okay, so this becomes an integral of, and I've got a k, got a sigma, and in place of dA now, I have 2 pi r dr over the square root of r squared plus x squared. And so finally, I can get to my calculus, where I can actually do the calculus. So all of this was kind of more reading of the calculus. You know, it was back here and trying to understand the physics. I'm adding up a bunch of rings to get a disk. This is the potential of a disk. This is how I change it to an integral, and it means a dq. How do I get rid of the dq? I can change it to a dA through this transformation. How do I get rid of the dA? Well, I can change it to a dr through this transformation. So that would change everything from a DQ to a DA to finally a DR, something that I actually can set the limits of and say, okay, we're going to add up from 0 to capital R. These are going to be our rings. So it takes a little bit of work and understanding and, again, reading the math in order to get to this step. Now we're at the quote-unquote easy part because we can... And let me remind you that sigma is a constant times an R, CR. So, like any good calculus problem, let me pull out the constants. So Coulomb's constant and then this C. I got to leave the little r in there, that changes. The 2 pi can come out. But I get an r squared dr on the top. And downstairs I have the square root of r squared plus x squared. And we're going from 0 to capital R. And so that's our integration. So these are our limits. And that's why I was saying that this is a pretty hard integral. Because... like I said, maybe now you can see it if you wrote this as r dr and the square root of r squared plus x squared, you can see that this is the differential of that. So this you can set to du, this to v, and do your integration by parts. So that would equal uv minus u dv. And so instead of trying to do that one, you do that. And that too is tough. This actually comes out pretty easy. But then this one has the du of this has a trig sub. But again, I'm going down the road of actually solving the math. I'm trying to convince you, don't actually solve the math. Look this up. And a little disappointed that the textbook didn't have this one in the Appendix B. They have a lot, and a lot of good ones. And I don't think I've ever noticed this before, because I thought everything I've ever come across in this textbook I could also look up in the Appendix B. But this one I could not. And then I remember that. I think a couple years ago I remember working with some students in the office and coming across this and couldn't find it in the back of the book, so I got out one of my math books that had a much more thorough table and looked it up. But as I said, I couldn't do that at home, so I'm going to maybe bring that math book home for me. But I did look up on the internet, and I looked around for a while. Had trouble finding it, but finally found it. This is the one we would want. So I guess we've got to be kind of careful with our notation. This x squared would really be my r's. So everywhere you see an x, I will place it with an r. And this x is the thing that doesn't change for the rings, and so everywhere in this problem that you see an a, I'll put an x. So, like I said, that can get confusing because the x's in this problem mean r's, and the a's mean x's, and that can be a little confusing. But nonetheless, I think I have it, and so I'm going to do this integral. So I will put a 1/2, and I'll say it again. Everywhere I see an x, that should be an r, and everywhere I see an a, that should be an x. All right, so this would be r times the square root of r squared, and I want the upper one, so the plus, the upper one, and that would be then x squared. And again, I want the plus, so I want there it is, the upper one, and so I'll put a minus here, because that's the upper sign, minus. And then there's a 1/2, and then there's an a squared. Now remember, where we've seen a, we put an x, so that's x squared. And then this is the natural log of the absolute value. Again, everywhere we see an x, we put an r, so there would be an r plus a square root of r squared plus, and again, we would use the upper sign because that's the one we want. And then everywhere I see an a, I'd put an x. Okay, and I need to evaluate this from 0 to capital R. So this would be kc2 pi. And let me put in a capital R. So this would be a 1/2 capital R square root of capital R plus x squared minus 1/2 x squared, natural log, capital R. I'm just going to drop the absolute values because these are all positive numbers. They wouldn't be negative. So this would be an R plus an R squared plus an x squared. And that would be putting in the R. So then I would subtract, putting in a 0 for R. Well, put in a 0 here. That one's 0. And so the whole thing is 0. And again, if I put in a 0 for R, that one goes away. That goes, and I just have then the square root of x. And again, technically absolute value, but again, going back to our picture, this is a distance away. It's a positive number. So I'm just going to write it as an ln of x and drop the absolute value. And I hope we get the same thing that's in the back of the book. So this is a 1/2 an R times the square root of R squared plus X squared. Maybe I will factor out a 1/2 X squared and then have an ln. And it looks like, if I factor out an ln, that would be, well, that minus with that minus makes the whole thing plus. So if I factor out a minus, then it's minus this quantity. So I'll take properties of the logarithms and go R times the square root of R squared plus X squared over X. Wow. And that's is a heck of a problem. All right. Take care.